In this lecture, we discuss about relativistic quantum mechanics, the Caylin-Gordon equation. Caylin-Gordon equation. The two standing achievement in theoretical physics, namely relativity, the Einstein proposed, and quantum mechanics, Schrödinger and Heisenberg, the synthesized the relativistic quantum mechanics, special relativity and quantum mechanics. In doing this, we must respect Lorentz covariance. In non-relativistic quantum mechanics, the description of a point particle poses no difficulties. It is possible to localize arbitrarily accurately a particle in space-time. In relativistic quantum mechanics, of one particle, it cannot be localized in space within the volume of linear dimension less than h divided 4 mc. Since otherwise the energy of the particle, approximately p square divided 2m, will be greater than 2mc square, which can be seen as delta p greater than h divided 2 delta x equal to 4 mc h divided 2 h equal to 2 mc, and delta p whole square divided 2m equal to 2mc square. Suffice to produce a pair of particles, the upper limit of the velocity in the relativity is responsible for this. So Schrödinger developed his non-relativistic wave equation in 1926. In the same year, he proposed extension of the incorporating special theory relativity. It easily seen for a free particle whose non-relativistic relation E equal to p square divided 2m, with the standard limit or substitution, the standard substitution E is del by del t and p minus I square gradient. Yielded, we have I h square del psi by del t equal to minus a square divided 2m Laplacian psi, and the relativistic equation is E square equal to p square c square plus m square c to the power 4. Else we can substitute it E and p, so we have minus square del square psi divided del t square equal to minus a square c square psi plus m square c to the power 4 psi. This is one equation. And the above equation is for the free relativistic particle has the plane wave solution of the form psi of r vector and t e to the power I k dot r vector minus omega t. This is 2, which is eigenfunction of the operator E and P with the eigenvalue h car omega and h car k, and P h car k. Then the one equation can be written as h car omega equal to plus minus root under h car square c square k square plus m square c to the power 4. The positive and the negative square root correspondent to the ambiguity in the sign of relativistic energy momentum relation for the energy. Postponing the negative energy solution, let us restrict ourselves to positive energy solution and multiply the one equation left hand side by psi star and right hand side this complex conjugate equation by psi just then we have and then rearrange it and we have the continuity equation del by del t rho of r vector t plus divergence of s r vector t equal to 0 where rho of r t equal to I h car 2mc square psi star del psi by del t minus psi del psi star by del t and s r vector of t equal to h car divided 2 im gradient of psi minus psi gradient of psi star. This is equation number 3, this is equation number 3 and this is equation number 4. Rho is the charge density and S is the current density as in the non-relativistic quantum mechanics. The expression rho is not in the expression for rho is not quite the non-relativistic one, which is mod psi square is positive probability density, but this is the equation 2. Here is the equation 2 restricted to positive energy solution. We have psi equal to e to the power I k dot r vector minus et divided h car. From E we can subtract the rest energy of the particle mc square so that E prime equal to E minus mc square and E prime less than mc square. Then psi equal to the power I k dot r vector minus E prime t divided h car and e to the power minus I mc square t divided h car, which can be written as phi of r t e to the power minus I mc square t divided h car. Then the time derivative on phi will pull out E prime, which is begin much smaller than mc square, can be neglected in comparison with the time derivative of e to the power minus I mc square t by h car. Then the expression for the rho is mod phi square as the non-relativistic quantum mechanics. And the equation number, then the equation for rho, equation number for necessarily not positive, there here is the rho is necessarily not necessarily positive because the one equation is second order equation in the time derivative. Then psi and del psi by del t are independent. To determine the change of the wave function with the time, we need to know value of the both the function if its first derivative with respect to the time at a given instant. If t equal to 0, this is 2 are chosen, so the rho is positive. There is no guarantee rho is remain positive at the later time. Okay, so it is not possible to interpret the rho probability density or well defined value particle coordinate. So rho can be positive and negative, but probability density could not be negative. Okay. Now another features of the one equation, this is the one equation, another features of the one equation, applying proper Lorentz transformation, we see that one equation is invariant, so that the wave function can at most differ by plus minus 1. Apply parametric operation, we see that the wave function could be either the wave function could be either psi of rt equal to psi of minus r vector t is a scalar, and psi of r vector t equal to minus psi of minus r vector t is pseudo scalar. Scalar or pseudo scalar function described as the particle zero spin with the zero spin. Here the spin is 0, so that the one equation cannot describe the electron. So the Kelvin-Gordon equation cannot describe the electron. Zero spin particle it describes. Okay. So one equation proposed by Kelvin-Gordon equation independently in the same year of 1926. Much later, it realized that in the context of the field theory, it can be represented pions. If we restrict the positive energy along and take the relativistic energy relation as E equal to root under p vector c square plus m square c to the power 4, then one can get the quantum as I h car del psi by del t root under minus c square h car square psi plus m square c to the power 4 psi. Then the first order time derivative equation is arise. Then however the right hand side involved operator inside the square root. The Kelvin-Gordon equation acquire importance in the description of the relativistic scalar field. To see the importance we can recall. The interpretation of the rho as a probability density was futile. We multiply rho by E and consider rho equal to I h car divided 2 mc square E psi star del psi by del t minus psi del psi by del t, this would be charge density which can be positive, negative or 0. So then the solution can be written as n e to the power I by h car p dot x minus et. Writing this for positive negative energy, we can have psi plus minus equal to n plus minus e to the power I by h car p dot x minus plus mod et. Okay. So the above equation shows that we can interpret psi plus representing the particle with positive charge and psi minus as the particle with negative charge, same mass. So to describe the zero charge, psi can also be real. It follows then psi can also be real. This is equation number 7 and this is equation number 8 and this is equation number 6. Okay. So one can express the Kelvin-Gordon equation in the Schrödinger form as something I h car del psi by del t equal to h psi with h equal to tau 3 plus I tau 2 p square divided 2m plus tau 3 mc square, where tau 1, tau 2, tau 3 are the Pauli matrices. Tau 1, tau 2, tau 3 are Pauli matrices. This is the equation number 9. By acting once again the first equation by I h ka del by del t and using a square equal to p square c square m square c to the power 4, we can recover the Kelvin equation more details. We can continue the Schrodinger equation form. Note that the Hamiltonian simply above. H equal to s square divided 2m 1 1 minus 1 and mc square 1 0 0 minus 1. Here this is the 2 cross 2 matrix, so it is responsible to consider psi equal to phi and chi. Phi and chi on which phi and chi, this is equation number 10 and this is equation number 11, on which H acts. It is seen that each component of psi satisfies the Kelvin equation. Substituting this on the 10 equation and 11 equation, we have IH car del phi by del t equal to minus h square divided 2m Laplacian phi plus chi plus mc square phi and IH car del chi by del t equal to h square by 2m Laplacian phi plus chi minus mc square chi. This is equation number 12. Adding these two equations and we can get IH car del pi del t phi plus chi equal to mc square phi minus chi, and subtracting this equation we can get adding, this is adding, add and subtract, we can get minus h square, so del square divided del t square phi plus chi equal to minus h square c square Laplacian phi plus chi plus m square c to the power 4 phi plus chi, which can be the Kelvin equation upon identifying psi equal to phi plus chi. So this is equation number 14 and this is equation number 14 and this is equation number 15. So 11, 13 and 15 can be expressed as rho equal to E phi star phi minus chi star chi and E psi dagger tau 3 psi. What is happening? In the quantum mechanics, the wave function depends on the space and time coordinate. If there are additional degrees of freedom required for discrete variable which is observable mostly, we amend the wave function as a column vector of several components. Recall our experience with the described spin. The Kelvin-Gordon equation describes spin 0 particles and column vector behavior in the psi corresponding to the additional degrees of freedom associated with the charge. As charge has two values, there are two components here which we will enlarge in these topics. It should be emphasized now that though this 9 equation we have succeeded in the removing the painful square root, the square root 1.5 the 5 equation and reveal the temporal and spatial part treatment differently. We will remove this in the next lecture, which is the Dirac equation. The Kelvin-Gordon equation with potential. The Kelvin-Gordon equation with potential. The Kelvin-Gordon with potential. So far we consider Kelvin-Gordon equation for a free particle. Now we consider it with the potential. In non-relativistic mechanics, we can simply add the potential to the kinetic energy, which is p square divided 2m plus v. In relativistic quantum mechanics, we implement this by replaced by p minus ea vector and e minus phi. Then, where A and phi the electromagnetic potential, we can obtain E minus phi whole square psi equal to minus I h square minus E a vector whole square c square psi plus m square to the power 4 psi. We restrict to the case for which a vector equal to 0 and phi equal to v of r, the spherical symmetric potential function. Then the above equation can be written as E minus v of r whole square plus h square c square gradient of minus m square to the power 4 psi equal to 0. For stationary state, it can be verified that the operator, this is equation number 18, this is the operator in 18 equation commute with the orbital angular momentum. So the L is the good quantum number. Hence we can justifiably try to separate the variable as psi r theta phi equal to r of r and y ml theta phi, where phi stand for the azimuthal angle. This is equation number 19. It means that effect of the relativity in contained in r of r, and 19 and 18 equation. For 19 and 18 equation, we arrived at the following equation of r of r: d square r dr square plus 2 by r d by dr plus e minus v of r whole square divided h square c square minus m square c square divided h square minus l into l plus 1 r square r of r equal to 0. Our object is to solve the radial equation. So we choose v of r to be the Coulomb potential for hydrogen like atom. So v of r equal to minus z e square 4 pi epsilon naught r equal to minus h square c z alpha divided r, where alpha is e square divided 4 pi epsilon h square c, where alpha is a fine structure constant which is 1 by 137. And let's naming the equation. This is 20 equation, this is 21 equation, and this is, and so the 20 and 21 equation we can rearrange it, and we have d square r divided dr square plus 2 divided r dr divided dr f plus 2h divided r plus g divided r square are equal to 0, where f equal to 1 by h car square e square divided c square minus m square c square, h equal to e z alpha divided h car c, and g equal to minus l plus 1 minus h square alpha square. We can now introduce the dimensionless variable rho equal to 2r root under minus f. Then equation number this is the equation number 22, and this is equation number 23, and this is equation number 24. The bound state energy of the hydrogen like atom will be less than mc square, so mod E less than mc square, and so minus f greater than 0. To ensure that rho is positive like r, then this 22 equation we can written as becomes d square r of rho divided d rho square plus 2 by rho dr of rho divided d rho plus minus 1 by 4 plus h divided rho under minus f plus g divided rho square r of rho equal to 0. This is 25 equation. For the bound state, we require r of rho tends to 0 as rho tends to infinite. So we write r of rho equal to the power minus rho by 2 f of rho. This is equation number 25, and this is equation number 26. So equation number 25 will give the following equation f of rho. We have d square f divided d rho square plus 2 by rho minus 1 df by d rho plus h divided under minus f minus 1 by rho plus g divided rho square f equal to 0. We attempt a series solution of the form f of rho equal to rho to the power summation nu equal to 0 to infinite a nu rho nu a not equal to 0, where s is to be determined. This is equation number 28, and this is equation number 27. Where s to be determined, substituting this on the 27 number equation, we obtain in summation infinite nu equal to 0 a nu is s minus 1 plus 2s nu plus nu minus 1 plus 2s plus 2 nu plus g rho to the power nu minus 2 minus a nu s plus nu minus h root under minus f minus 1 rho to the power nu minus 1 equal to 0. The coefficient of the every power of the rho must be vanished. We equate the coefficient of the rho to the power nu minus 2 to 0 to find a nu equal to s plus nu minus h divided under minus f divided s plus nu whole square plus s plus nu plus g a to the power nu minus 1. A recurrence relation for the coefficient. This is equation number 30, and this is equation number 29. We can simply the equation number 30. First, the wave function must be finite as rho tends to infinite. This is the achieved by the terminating the series. Let the series terminating nu equal to n prime, so that a n prime plus 1 equal to 0. Then this equation number 30 can be written as s plus n prime plus 1 minus h divided root under minus f equal to 0. So the equation number 30, we set n equal to 0 and a minus 1 equal to s square plus s plus g divided s minus h divided root under minus f a naught. So equation number 28, we have a minus 1 equal to 0. We can find that s plus 1 equal to minus g. So equation determining the s and a nu equal to nu minus n prime minus 1 divided nu plus 2s plus 1 a nu minus 1. This is equation number 33 and this is equation number 32. So 33 equation, we find a1 minus a prime 1 plus 2s plus 1 a naught a2 plus n prime minus 1 divided 2 into 1 2 plus 2s plus 1 plus 2s plus 1 a naught and a3 minus n prime minus 1 and n prime minus 2 a naught 3 2 1 3 plus 2s plus 1 2 plus 2s plus 1 1 plus 2s plus 1 and a nu equal to minus 1 to the power nu n prime factor 2s plus 1 factor divided n prime minus nu factor nu prime factor nu plus 2s plus 1 factor a naught. This is equation number 34. So the 28 and 26 equation, the number 26 equation, the radial wave function is given by r of rho equal to a to the a0 e to the power minus rho by 2 rho to the power s summation nu equal to 0 to n prime minus 1 to the power nu n prime factor 2s plus 1 factor divided n prime minus nu factor nu plus 2s plus 1 factor to the power nu, where rho equal to 2r root under minus f. This is equation number 35. Determining of the s, so we have s equal to minus 1 by 2 plus minus root under L plus 1 by 2 whole square minus z square alpha square from the equation number 23 and equation number 32. Then we have the parameter s cannot be negative, so we should make that the 28 number equation singular near the origin, so that the positive square root, then we have s equal to minus 1 by 2 plus 2 under L plus 1 by 2 whole square minus z square alpha square. This in the non-relativistic limit s equal to L as it should be. However, for L equal to 0 state and s is the negative. This is equation number 37. This is equation number 36. We find E equal to mc square divided under 1 plus z square alpha square s plus n prime plus 1 to the power minus 2. This is equation number 38. After substituting for s, the 37, this value of the s, and we have the equation E equal to the energy equation mc square divided root under 1 plus z square alpha square 1 plus L plus 1 by 2 whole square minus z square alpha square 1 by 2 plus n prime minus 2. This is equation number 39. In the above expression for E, n prime is the power of rho after which is the series for R terminated. In the order to make sense of the complicated expression, we proceed to expand and keep it up to alpha to the power 4 consisting. First we consider L plus 1 by 2 also minus a square alpha square 1 by 2 equal to L plus half 1 plus 1 minus L plus 1 minus a square alpha square divided L plus 1 by 2 whole square 1 by 2. Then L plus 1 by 2 1 minus z square alpha square divided 2 L plus 1 by 2 whole square minus 1 by 8 z to the power 4 alpha to the power 4 divided L plus 1 by 2 to the power 4. And we have L plus 1 by 2 minus z alpha square 12 plus 1 minus z to the power 4 alpha to the power 4 divided 12 plus 1 to the power cube. Here we have 1 plus x to the power a 1 plus ax plus a minus 1 divided 2 factor x square something. So this equation can be written as n equal to n prime plus L plus 1. So E equal to mc square divided root under 1 plus z square alpha square n minus z square alpha square divided 12 plus 1 minus z to the power 4 alpha to the power 4 divided 12 plus 1 whole cube to the power minus 2. So it can be written as mc square 1 minus 1 by 2 z square alpha square divided n minus z square alpha square divided 12 plus 1 minus z to the power 4 alpha to the power 4 divided 12 plus 1 whole cube whole square plus 3 by 8 z to the power 4 alpha to the power 4 divided n minus z square alpha square divided 12 plus 1 minus z to the power 4 alpha to the power divided 12 plus 1 whole cube to the power 4. So this is equation number 41. The 41 equation expanded up to alpha to the power 4 as z square alpha square divided n minus z square alpha square divided 12 plus 1 minus z to the power 4 alpha to the power divided 12 plus 1 whole cube approximately z square alpha square divided n square plus 2 z to the power 4 alpha to the power 4 n cube 12 plus 1 and z square z to the power 4 alpha to the power 4 divided n minus z square alpha square divided 12 plus 1 minus z to the power 4 alpha to the power divided 12 plus 1 whole cube to the power 4 approximately z to the power 4 alpha to the power 4 divided n to the power 4. So equation 41 becomes, this equation became, we have E minus mc square equal to minus z square alpha square mc square divided 2n square plus z to the power 4 alpha to the power 4 mc square 3 by 8 n to the power 4 minus 1 by n cube 12 plus 1. This is equation number 42. The first term of the 42 similar as the Bohr term and for the energy state, and the second term is the relativistic effect. The second term involve L, and L is the degeneracy and the L degeneracy is removed. So the equation number 37 expresses the for S conjunction with the equation number 35. For the L equal to 1, it is seen that S approximately 1 minus z square alpha square divided 3 minus z to the power 4 alpha to the power 4 divided 27. This is the positive even up to z equal to 137, so that R of rho will not be singular near the origin. However, L equal to 0, we find S minus z square alpha square minus z to the power alpha to the power 4, which is negative. This is the problematic for the behavior of R of rho near origin. In the particular, the determination of the constant A naught by normalizing will appear to be difficult. So, we reconcile this by the noting the measure of the integration is rho square d rho. So, we have integration 0 to infinity r square of rho square d rho equal to 0 to infinity e to the power minus rho e to the power 2 minus 2z square alpha square minus 2 z to the power 4 alpha to the power 4 d rho, which is equation number 43, is convergent. The second term of the 42 equation, can be seen to the agreement with the first order perturbation theory calculating of the correction to relativistic kinetic energy to reveal that the hydrogen atom in the non-relativistic case, writing the relativistic kinetic energy is something p square c square plus m square c to the power 4 minus mc square, and the correction is p square by 2m minus p to the power 4 divided 8 m cube c square. So for the hydrogen atom, H not equal to p square divided 2m minus e square by r, and H prime equal to minus 1 by 2m c square H not plus e square by r whole square. The first order correction involves only the radial matrix element of 1 by r and 1 by r square. From this, it is easily to find the first order correction is minus mc square alpha to the power 4 divided 2n to the power 4 2n divided 12 plus 1 minus 3 by 4, which is coincident with the second term. We note that the above expression of the energy level of the hydrogen-like atom is inadequate as the electron spin taken to be 0, which is not to be the correct. Above expression can be applied pionic atom, which is electron replaced by the negative pion. With the use of m of mass of the pion is 140 mega electron volt, nearly 280 times the mass of the electron. Okay. So, thank you. Please like, share, subscribe. Next lecture of the relativistic quantum mechanics, we can discuss the Dirac equation and all matrices. Okay. Thank you. Please like, share, subscribe.